This is Greg Troutwine with Marine Technology TV, and we're very pleased to be joined today by Luc Lenane of Scripps Institution of Oceanography and Paul Devine of Teledyne Marine to discuss the Sub-Mesoscale Ocean Dynamics and Vertical Transport Experiment, or as it's better known, the SMODE project. Luc, if you can you start us off with a brief career biography with insights on your title and your current area of responsibility?
Sure. Yeah. So my name is Luc Lenane. I'm the current director of the Air-Sea Interaction Laboratory at the Scripps Institution of Oceanography. I am a physicist with a strong focus on observational sciences. And really, in a nutshell, what I try to do is to develop better understanding of the coupling between the ocean and the atmosphere. And in particular, I'm very interested in the role of surface wave breaking, and all those processes, upper ocean processes that will lead to turbulence, to all kind of small scale to larger scale physical processes that will have an impact on larger scale understanding of the ocean.
Well, that's excellent. Well, if your job is understanding that interaction between the ocean and the air, it sounds like the SMODE project was a perfect one for you to be involved with. So for those who are watching and reading that don't know of the SMODE project, can you give us a concise overview?
Sure. So the SMODE project really started with this idea that, to better understand and to better model the Earth's climate system, as computer capability has improved, we're getting to higher resolution. And higher resolution meaning that you can resolve much smaller scale processes, 10 kilometers. And in the ocean, you have those things that we call eddies, that swirls around. You have fronts, you have a lot of processes at these scales that we don't understand very well. And what the community has been realizing is that, we think that there is a role that those processes that we call sub-mesoscale processes, and that's why SMODE is called like this, actually play a role, and really an important role. I need to be better understand to improve our prediction of the Earth's climate system. So to develop a better understanding of the physical processes at the sub-mesoscales and how it fits with the larger scale processes, if you like, you need to collect observations. And collecting observation at those scales are extremely difficult. So the approach that we took by bringing in team with various expertise is to collect as much data from as many platforms as we can in a small area of the coast of San Francisco, and trying to observe all those processes, air-sea interaction processes, ocean dynamics, surface currents, et cetera, et cetera. So to do that, we use a lot of platforms. We use research aircraft, so that we can do airborne remote sensing of the ocean surface. So we have 3 aircraft that tells us about surface current, that tells us about waves, that tells us about ocean color, about ocean temperature. And while aircraft are great to provide good spatial coverage, it doesn't tell you anything about what's happening under the surface. So to do that, we use research vessel, we use autonomous surface vehicle, autonomous underwater vehicle, again, to try to collect as much observation as we can in this area on the dynamics of those processes, so we can develop a better understanding of the physics of what's going on.
But can you tell us a little bit more about the partners in the project, specifically some of the challenges that you saw in coordinating the underwater, the on-water, and the in-the-air assets?
Sure. So we have a number of universities involved in the project. We have Woodsole, we have University of Washington, a lot of more partners, and along with NASA groups, JPL is a central part of the project, flying 2 suborbital instruments, Doppler Scat and PRISM, as part of the project. it gets complicated, especially during COVID, to kind of organize and coordinate all those assets. But central to the project was to put together a core leadership team, and really try to put some emphasis on the communication between all the different groups, so that effectively what we created, a bit NASA style, is a control center, a mission center that really, that had the ability to gather real time all the data from all the different assets that were flying, that were deployed in situ, and make near real time decision on what to do next, which was very important.
Again, excellent, and I appreciate that overview. So, Luke, obviously, this project included a lot of technology. Can you provide a brief overview of the entire outfit of technological kit that was being utilized in the SMODE project to gather the information?
Sure. Again, central to the project are the airborne suborbital assets. There is a number of instruments that were flying. My group operates the MASS instrument, which stands for Modular Aerial Sensing System. It's an instrumentation package that is designed to gather very detailed, high-resolution observation of surface wave, kind of like swaths of surface wave, along with ocean color, hyperspectral imagery. We have LiDARs, we have various sensing capability within a small package to get information about the surface condition. Doppler scat is another instrument. This is a JPL, Jet Propulsion Laboratory instrument, and it's designed to produce map of ocean surface current and surface winds over very wide swaths in the order of tens of kilometers, which is really important when you start looking at those eddies, and those kind of sub-mesoscale features. You want able to capture their space, their lateral extent, and how they evolve in space and time. We had PRISM, which is an hyperspectral system that measure ocean color. So I start with the suborbital instrument because one of the other goal of SMODE is once you have observation of the ocean surface, can you actually tell something about what's happening underneath? How do you relate those surface observation to the underlying ocean dynamics? And that's an important goal for SMODE, especially in the context of future NASA mission. You can envision that some of those instruments will be transitioned to an orbital satellite system. What kind of science you can get out of those surface observation. So to do that, we also had in situ assets. We had underwater gliders that measured information about salinity, density, temperature over a broad range of depths. We had various drifters that tells us information about currents and convergence zones and those swirls and small eddies that I mentioned. We had sail drones that were outfitted with atmospheric and upper ocean observation and current profile, especially, which is really important for this project. And we had a fleet of wave gliders that it was a collaboration with Woodsole. So we kind of like collected our assets, my group's asset, and there was a group of Tom at Woodsole. And we built this fleet of wave gliders that were specifically instrumented for air-sea interaction and upper ocean process. And finally, we had a research vessel, so we did more traditional sampling as well, of biology and temperature, salinity profiles, and that kind of things. And the key here is, by having those collocated coincident observation of the ocean surface and those observation at one point, with in situ assets, we're trying to bridge the gap, trying to develop better understanding of the physics of the very upper ocean, so that effectively, hopefully at some point we'll be able to say something about the deeper ocean, if you'd like, or the ocean, like upper ocean dynamic, just from the surface observation that you could get, ultimately from a satellite.
So, Paul, I really appreciate you joining the conversation as well. I understand that Teledyne Marine has been a key technology partner in the SMODE project. Can you give us an overview of the specific Teledyne Marine tech that was used?
So, starting with Luke's wave glider, there's a 300 kilohertz ADCP that's capable of measuring the upper 100, 150 meters of the water column, so that you can begin to couple or to understand the coupling between the surface conditions and those that are going down, within the area where the ocean's accepting all the heat from the atmosphere. Right, Luke? I mean, it's about an air-sea interaction study, and we're looking at, you're looking specifically at lengths of these eddies that are a kilometer in length or smaller. And the ADCP does a very good job at understanding the vertical variation of those eddies from the surface that's sensed by the remote sensing down into the deeper ocean depths. So we're kind of responsible for we're contributing to the understanding of the coupling of the atmosphere and the ocean. I'm sorry, we're on the liquid robotics wave glider. We're also on the sail drone vehicle. We're also on the Oceanus, their research vessel. So we're on 3 of those platforms. So that's the kind of RDI's contribution to the SMODE is providing the velocity, current speed from near surface to down beyond 100 meters depth.
So, Paul, staying on the Teledyne Marine thread, how does this particular project resonate with the book that was released by Teledyne last year, the Ocean Book, which discusses the organization's impact from deep space to the deep ocean?
The Ocean Book, we talked about some of the early use of our ADCPs were in providing that verification of the ocean velocity that some of these remote sensing techniques would attempt to measure. And as Luke's saying, this new Doppler radar system is going to be pretty interesting if it can be deployed from a satellite. You have continuous swath coverage all over the entire ocean. We have provided since the 80s, when the first ADCPs were deployed at the equator as part of the El Nino prediction system. We've been providing measurements of the ocean's response to atmospheric forcing. So it's just I don't want to say more of the same, but Luke has taken those technologies onto mobile assets so that he could survey over space much more effectively and these sub-kilometer scale eddies.
I will say that Teledyne ADCPs have been an important instrument in the project, because they provide ocean currents, from a few meters depth down to up to 100 meters, and that's really important. That gives us a big picture. The things, those Sub-Mesoscales that I mentioned before, they're on the order of 1 to several tens of kilometers. And one of the characteristics is that they evolve very rapidly in space and time. So putting a mooring and attempting to study those processes is not sufficient, because you only have 1-point measurements. So one of the things that we've done as part of the project is use those ADCP sensors, those current profilers, and install them on those autonomous surface vehicles that moves around. We can remotely control them and tell them to go various places and do transect, for example, through those eddies and all those things like that. And as part of the project, one of those things that we did was also validating the ability of this sensor technology to provide good observation of current profile. So, as a scientist, it's one thing to collect observation. It's another thing to collect observation that are meaningful, that have the right accuracy to study the process that you're interested in. And that's something that we've done actually as part of the project, and concluded that the ADCP, those ADCPs were sufficient, had sufficient accuracy to resolve the physical processes we're trying to study.
So Luke, if I understand correctly, the actual activity of the measuring for the SMODE project is complete. Quite simply, what's next?
So it is actually not complete. We had a lot of delays associated with the COVID pandemic. So we ended up conducting our first experiment, which is technically a pilot program, with a 1.5 to 2 years delay. So we conducted this pilot program in October 2021, just a few months ago, and we have 2 more experiments scheduled. One in October 2022 and a second one in April, May 2023. So we're trying to get different seasonality, if you like. So though the program, I started, I think now 3 years ago, we're really just beginning to do science and look at some of those processes.
Luke, can you share with us any interesting findings or biggest surprises to date?
Sure. So again, this is very new. We just completed the experiment in mid-November, so just a few months ago. But we obviously picked a location of San Francisco that we knew based on a lot of climatology studies and numerical computer simulation of ocean currents, if you'd like, in the areas that this area was prone to have a lot of sub-mesoscale activity. We collected a lot of data and everything went really well. There were challenges because of the weather. So, like the experiment fell right at the time there was this bomb cyclone that hit San Francisco. But it gave us a little broader range of environmental conditions to deal with. But I think from my standpoint, and again, this is just looking at the data that I've collected, one thing that is really striking is how much temporal variability you see with those kind of processes. Those things are, those small scale, sub-mesoscale features, eddies and front, are really moving very rapidly, which is really exciting and very interesting, and really I think is going to be helping us better shaping the next round of experiment. The other thing that was really nice is, for me as a great result out of this experiment, multi-investigator, multi-institution, multi-disciplines, big program like this works. It was a pleasure working with everybody, and everybody was really, in terms of the coordination, it worked really well, despite some of the constraint, which is not always a given.